Okay, hi everyone. So this is about chapter 5, and here we're gonna, instead of doing a linear map from some vector space V to another space W, we call these linear maps. But if we have a linear map where T goes from V back to V, it gets a special word operator. And the reason is we can prove a lot more about these because we can do polynomials of an operator. What does that mean? It means we can we can do the operator twice. We can go from V to V and then just go from V to V again by doing T again. We couldn't do that over here because we'd be in, after doing T once, we'd be in W. We can't do T a second time because T has to eat vectors in the space capital V, not W. So this is a big thing. It means that we can do things like T squared minus 3 times T plus 5 times the identity. So if we had a polynomial x squared minus 3x plus 5, well then we'll just write P of T because we will want to do things like T squared minus 3T plus 5 times the identity. What does that mean? It means we can do P of T is now a new operator. If T mapped V to V, then P of T will map V to V. It's a new operator constructed from the old one. What does it do? Well, it takes a little vector, little v, and it sends it to T of little v minus, so this is a vector, so we can subtract vectors. We can scale T of v by 3 and then subtract these two vectors. We can just do this. Plus 5 times the vector. The identity map, remember, I of v equals v. Okay, so this is really important, and that's the word operator. Now, what if, so if U is a subspace of V, then what we can do, we can restrict T to U. What does that mean? It means just feed T things in U. Okay, so this deserves a new name, T, a big line, sub U. That will go in general from U possibly back to the bigger space V. And then we would not call T restrict U, we say it T restricted to U, it wouldn't be an operator. But if U is special for T, what do I mean by special? If for all little u's in U, we have TU is back in U again, then we don't have to go to the bigger space V. We can actually go from U to U. And now T restrict U is an operator on U. Okay, so the key here is that we will understand operators by understanding them on smaller pieces of the full space and then piecing it all back together. Okay. So this is called an invariant subspace. Invariant subspace. U is this definition here. So, and we'd say like U is invariant under T, meaning that T takes vectors in U and maps them back into U instead of possibly outside of U into the bigger space. Okay, so that means U is very special. All right, so for instance, if we have an operator T, then null of T is invariant under T. So proof, let little x be in null of T, then is Tx back in null of T? If yes, then it's invariant. So Tx equals 0, but null T is a subspace. So 0 is in null T. Okay, so the null space is invariant under T. Also, the range of T is invariant. So let W be in the range of T, then W is equal to TU or TV for some V in V. That's the definition of being in the range. But actually, we won't even need that. All we need to check is just is TW in the range? If yes, then the range of T is invariant. Well, yeah, the range is defined. So remember, the range of T is defined as the set of all things that look like TV for V and V. And W is in V because W is in the range, and the range, and here's where we need an operator. Remember, typically the range would be in the output space, which might be capital W. So it wouldn't be in V again. But here again, we have the special case where we're going back to the same space itself. And then the range of T is a subspace of V, just like the null of T is a subspace of V. That's very special for operators. If we had T from V to W, then the range of T would be a subspace of W, and the null of T would be a subspace of V. But we're not. We're doing more special things now. Okay. So, in fact, why don't we just go ahead and prove that? Well, no. Let's wait. Okay. So, what are some key results in this chapter? Well, first, we need to know what eigenvalues and eigenvectors are. So, if V is non-zero and TV is lambda V for some lambda in the field, then we say that V is an eigenvector with eigenvalue lambda. Okay? And V non-zero is important. And what we're really seeing here is that the span of V is a one-dimensional invariant subspace. Because if you take something in the span of V, it looks like CV for C, a scalar. And then if you apply T to it, well, T is linear, so we can pull the scalar out. And then TV is lambda V. And so that's just some scalar C lambda times V again, which means that this is in the span of V. So if you start with something that's in the span of V, it stays in the span of V, and that is the definition of invariant subspace. And it's very special because it's one-dimensional. So this is like the best possible case, is that you literally have a one-dimensional space that just goes right back to itself. It just gets scaled by some number, 5 or negative 2. Right? So if lambda was negative 2, that still stays in the same subspace, and negative 2 would be the eigenvalue. Okay. So it turns out that one of the most important results in this chapter is that eigenvectors with distinct eigenvalues, distinct means they're not equal, eigenvalues are independent. So they're linearly independent. So what's the proof? So let TV1 equal lambda 1 V1, TV2 equals lambda 2 V2, etc., all the way up to TVN equals lambda n Vn, where lambda 1 is not equal to lambda 2, and lambda 1 is not equal to lambda 3. I'm saying that they're distinct, and in general, and lambda I is not equal to lambda j unless I is equal to j. So they're all distinct. Now we have to prove they're independent. So how does a proof of independence work? We say, suppose that there's some linear combination AI of, no, not TVI. I want to show that the eigenvectors are independent. I'm showing the eigenvectors are independent. Okay, now suppose this is some linear dependence using all n of them. I decided that there were n of them, whatever. Throw away any 0 terms. So some of the a sub i's might be non-zero. Just throw them away. Get a dependence. So this equation is called a dependence of minimal number of non-zero terms. The proof strategy is we're going to apply t to this equation, and we're going to see that, well, actually, we're not going to apply t. We're going to apply a polynomial, t minus lambda 1 times the identity. That's what we're going to apply to both sides of this equation. And what we're going to get is a dependence with one less non-zero term. And that contradicts the fact that we started off with one that has the minimal number of non-zero terms, let's say m terms. So then we would have a sum through m equals 0. So I'll finish it. Apply t minus lambda 1 identity. Okay, so let's write this out. This starts out a1 v1 plus a2 v2 plus dot dot dot. If I apply this to both sides, I definitely get 0 on the right. So I still get 0 on the right. Now what do I get here? Well, I get t applied to a1 v1 minus lambda 1 I applied to a1 v1. And then that was just the first term. But let's see what happens here. I get a1 lambda 1 v1 because t hits v1 and it's an eigenvector with eigenvalue lambda 1 minus a1 can just pull outside lambda 1 v1. In other words, I get 0. But only for the first term because I've picked out lambda 1 times the identity. And so only my first term goes away. That will give me a 0. But what about my second term? If I apply this, I'm going to get a2 lambda 2 v2 minus a2 lambda 1 v2 from here. Okay, and that's not 0. I can rewrite that as a2 lambda 2 minus lambda 1 v2. Okay, and then plus dot 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 equals 0. So what I'm going to get here is all the other terms are going to look like this, and that is not 0. But the first term went away and became 0. So now I have a dependence with m minus 1 terms, and that contradicts the fact that I chose my dependence to have the minimal number of non-zero terms. That contradiction finishes the proof. Okay. So that's an important result. Right away, a corollary of this. So corollary is a word that means it's like an extra result that is easy to prove now, that we just proved another one. Easy to prove using our previous result. What's the corollary? The corollary is that any operator has dim v, has at most dim v eigenvalues. Okay? And that's just because if it had more than dim v, we would have more than dim v independent eigenvectors. So you can't have, the number of independent vectors is always less than or equal to the dimension of the space. So that's why we know that there's at most that many eigenvalues. Because if we had more, then we'd have more independent vectors than we have dimension. Remember, the dimension is the number of vectors in a basis. And a basis spans and is independent. So this would be the maximum number of independent vectors is the dimension. Okay. All right, the last thing in the book is that it will be important for us is that if we take P of t and Q of t, then that's the same, or actually really if we have some polynomial like f of x, and f of x factors as p of x times q of x. For instance, like in chapter 4, we had that, like maybe it factors like x minus 5 times x squared minus 2x plus 2. What we want to do is to say that f of t, the operator f of t, which is now a new operator we constructed from our operator t, we want to say that it also factors as the operator p of t applied after the operator q of t. And because polynomial multiplication is commutative, like we can exchange, we could write this term first, or this factor first, and then the x minus 5 factor last. You can rearrange the order. We can also rearrange the order of our new operators, q of t, p of t. So this will allow us to take factorizations of polynomials from chapter 4 and turn them into factorizations of operators. Okay, and this is crucial. This is, operators are things that we can do. We can square them. We can to the third. We can add them together now, and so we can get polynomials in the operators because they have the same input and output space. And that means we can apply our knowledge of polynomials. And we know a lot about polynomials. We know exactly how they factor over R. We know exactly how they factor over C. Okay, so let's prove this result. So let's prove that if f of t, if f of x factors as p of x, q of x, then f of t, the operator, also factors as p of t, q of t. So this is an equation of operators. So to see if two operators are equal, you feed them a vector. Feed them some v and v. Okay? And see if they do the same thing to it. So let's give names to our polynomial. Let's say this is ai x to the I, so that means like a0 times x to the 0, but x to the 0 is 1. a1 times x to the 1, but x to the 1 is just x. a2 times x squared, a3 times x to the third, etc. And maybe this has degree m, okay? And let's give names to this one. Let's say it has degree n, and it's the b sub I x sub I, okay? Then how do we multiply polynomials? Well, the way you multiply polynomials is you just take all terms here and multiply it by every term here. And let's say I had the a3 x to the third term that was inside there, and I had the b2 x squared term that was inside there. I'd multiply these together when I multiply the polynomials, and I'd get an a3 b2 x to the 3 plus 2. Okay? So if I write that out sort of abstractly, then what I get is that I have a sum of ai bj x to the I plus j, and this is over all possible pairs of ij, where I goes from 0 to m and j goes from 0 to n. Okay, and I'm not going to write that in the sum, but so now I've given names to this. Now let's see. What we're going to do first is check what does f of t do to v. Feed this little v in v. Okay, so f of t then would be this thing, the sum of ai bj t to the I plus j. And it just eats the v, and it does t I plus j times. It does, if I plus j is 2, and it does t squared. It does t twice to v. And then you get some sort of vector here, you scale it by this number, and then you do that a bunch of times and you add up the result. Okay, that's done. Now let's do it to this side and see if we get the same thing. Let me choose a different color, green. Feed this little v and v. Okay, so then p of t is going to wait, and it's going to eat whatever q of t does to little v. Okay, so p of t is going to eat q of t. Now what's q of t? I replace x with t. Sum of the bi, or let's say bj, t to the j v. Okay, same thing. I just apply t j times. I get a vector, I scale it, and I add up all the results for the different j's. Okay, now what's p of t? P of t is this thing, but where I replace x with t. So this is now a sum. Okay, let's say j equals 1 to n equals 1 to m of ai ti, and that's going to eat this thing. But hold on a second. T, so this t to the I is maybe a t after t after t after, and it's going to eat all this. But let's take the first t that occurs here, and we're going to eat it, feed it this sum. But remember, t is linear. So it goes through the sum, it goes through, and the scalars pull out, and the sum pulls out, and the whole thing just becomes, basically this pulls through and goes there. So we get the sum ai, sum of the bj, ti, tj, v. But if you do t j times and then do it I times, guess what you get? T I plus j times. Okay? And so these are equal. So they do these two operators up here in this equal sign do the exact same thing to every input, little v. That means that they're equal as maps, as operators from t to t. Or sorry, from v to v. From v to v. Okay. All right. Now, once we have that, the last result that I'll point out is this fact that now we have more invariant subspaces. So let t be an operator. Let p be a polynomial. Let's say it doesn't matter what field, either the reals or the complex numbers. Then we know that p of t is now a new operator. Is a new operator. And here's the thing. The null space of p of t is invariant under t. And the range of p of t is invariant under t. So we started with an operator t, and we'd like to know invariant subspaces for it. And it turns out that for any polynomial, we can create a new operator, and immediately its null space and its range of this new operator is now also invariant under t. Okay, so let's see that. Let's see why. So let x be in the null space of p of t. And we're going to compute tx. And we want to see, is tx in the null space of p of t again? That's what we want to check. Well, how do we check if something's in the null space of p of t? Well, we apply p of t to it. So p of t applied to tx, that is equal to, and now because we can multiply polynomials in any order, we just proved I can flip the order here. I can first do p of t and then do t to x. But remember, x was in the null space of p of t, so now this is 0. And t applied to 0 is 0, because t is a linear map. So, yep, it's in the null space of p of t, because when we hit tx with p of t, we get 0. And that's what it means to be in the null space. I'll leave the range to you. It's equally easy. You just unpack the definition. But the point is now we're going to use this in proofs. So look for this in future proofs. Okay. Where we find invariant subspaces. And really what will happen is we're going to use induction on dimension. And the null or the range of p of t will then be a subspace of smaller dimension, where we'll, by induction, assume the result holds, and then we'll be able to prove it on a bigger space. So this will be really useful to to use induction on the dimension in proofs, in future proofs. Okay, you'll see what I mean later.